So my name is Hugh Gallagher, and I would like to talk to you about a project, computational modeling of a Seiche in a circular above ground pool. This is work that I did with two undergraduates, Benjamin Ware and Melissa Mary, who's now a graduate student at the University of New Hampshire. A Seiche is essentially a standing wave that is set up in an enclosed fluid body, such as a lake or bay. And an external force might be applied to the surface of the lake, causing one side of the lake to rise up. And then when that external force is released, the exchange of gravitational and potential energy between each end of the lake causes the surface to oscillate back and forth. We can set up the same thing in an above ground pool by driving the center of the pool vertically up and down at just the right frequency. We can set up a standing wave where there are antinodes in the center and the edge, and a node about 2/3 of the way out. In order to measure the period of this Seiche, we took a LEGO Mindstorm EV3 and an ultrasonic sensor and built a mount to hang over the edge of the pool, as you see here. We took data on the height level of the surface at 0.02 second intervals for a period of about 10 minutes. And here's a look at some of that data. On the vertical axis, we have wave elevation in centimeters relative to an average surface position. And on the horizontal axis, we have time in seconds. And you can see essentially that, first of all, we have oscillations, and then we have a decay period, and then a somewhat milder decay period. The strongest damping seems to be from 0 to 200 seconds. What Ben did was actually to take this data from 0 to 200 seconds, as you see here, and fit it to essentially a damped harmonic oscillator in order to extract the period and the amplitude and the time constant of the damping. And so here you can see the raw data in blue, and the red represents a fit to this function with a period of 1.975 seconds, an amplitude of 6.2 centimeters, and the time constant is roughly 340 seconds. So, how do we understand this oscillation? I'm going to move exceptionally quickly through some fluid theory here, but we have essentially the continuity equation, and then the momentum equations in the x, y, and z directions, and there's a gravitational term. The velocity vector has x component u, y component v, and z component is w. And the ddt is the convective derivative. And if we use a coordinate system where we have essentially the free surface is at z equals 0, the bottom is at z equals minus h, and eta is going to be the height of the actual surface relative to the free surface. If we use that in some approximations, the shallow wave approximation has the wavelength of the wave is much greater than the depth. Hydrostatic equilibrium Okay, and that gives us a relationship for the pressure. We linearize the momentum equations about a state of rest. We assume no friction, but later we'll add bed friction into a model. Negligible spatial variations in atmospheric pressure, small surface oscillations, so eta is much less than the depth, and uniform depth for this case, because that's the case with the pool. And we're also, when we transform to cylindrical coordinates, we're going to assume radially symmetric solutions. That's an awful lot of assumptions, but where we go with this is essentially we obtain the equation for an undamped traveling wave along the surface of the pool. And so this is the wave equation in cylindrical coordinates. And it can be solved by the separation of variables into a radial part and a time-dependent part. The time-dependent part is going to be a sinusoidal oscillation, and the spatial part is going to be a zeroth order Bessel function of the first kind. So now we're going to need some boundary conditions, and we know that out at the edge and in the center of the pool, the surface is not fixed. It's oscillating up and down. So the boundary condition we use is essentially a Newman boundary condition on the slope of the radial part of the solution. And what we want is for that slope to be zero. Well, the derivative, the spatial derivative of the Bessel function is going to give us a first order Bessel function of the first kind, and that needs to be equal to zero. Well, using that information, and the fact that the Bessel function, the first zero of the first order Bessel function of the first kind, occurs when the argument is 3.8317. So here we have that the period is 2 pi over omega, but omega is the speed of the wave times the wave number. And we replace the wave number using this relationship here. And if we run the numbers through, we get a period of 1.53 seconds. You might recall that that period is significantly less than the 1.975 that we observed. Well, part of the problem here is that our shallow wave approximation is not valid. H over lambda is going to be about 0.19, so it's about 1/5. So that means that H is not much smaller than lambda. Under these conditions, the wave speed is not the square root of gh, but it's given by this expression here. And so if we do this same calculation up here with the new speed, we come out with 1.83 seconds, which is approximately a 7% difference from what we observed in the pool. Part of my reason for doing this was I like giving students, upper level physics students in computational physics, interesting computational problems. And I think it is, after having gone through with them how to solve numerically the way the equation for a wave in a string, I think it's very interesting to go to solve the wave in the surface, on the surface of the basin in cylindrical coordinates. So here it is again. The only thing we've done this time is we've added in this damping term. Remember, there's a little bit of damping that's there. The damping time constant was about 340 seconds, so significantly longer than the 1.975 period. So frictional forces probably are not significant here. But if we use a zero order Bessel function to give us an initial condition and a finite difference scheme numerically, we can solve the above equation. And again, using a damping coefficient of about 0.006 seconds to the -1, so very small. And if we go ahead and solve this, we get the following figure. What we're looking at here is wave height in color code. And so that's actually the surface height. Time goes down this way. And space from the center of the pool out to the edge of the pool is on the horizontal axis. And so if you want to see what's happening in time at a given position, you can look at the vertical cross section. All right, so that would be essentially a vertical cut through here where we see that we're oscillating between blue and yellow. And here is that vertical cut, okay, and we see a very regular oscillation. As a matter of fact, it's got a period of 1.83 seconds, same as our theoretical calculation, and a very small amount of damping that doesn't seem to affect the period very much. If we go back to this curve here, you can see the standing wave pattern. When you see blue over here, okay, you see a bright, yellow over here, you see a bright yellow in the center. That's because the water is gathering in the center and it's very high there. You can see that we go through a pretty stable node here, and then we have another antinode here that's not as intense because the water has spread out among the circumference of the pool. But when this is down, this is up. So this is a very nice picture of what's happening within the pool. And of course, I think this is a nice picture, but the kids just think it's a wave pool. We started this with an initial condition of a Bessel function, and we've been trying to duplicate what we actually do in the pool, which is to drive the center. So here we did the same thing, but instead of having an initial condition, we started out with an initial condition of 0, just flat water, and we drove the center with a sinusoidal, a damped sinusoidal boundary condition. And you can see we get some of the same behavior, but as you go down in time, you can see we've got what almost looks like a little bit of beating, right? We've got strong color there, and then it weakens and weakens a bit more, and then starts to come back a little bit. Over here, we wondered what these shapes were like if you went and took a horizontal cut, because we should see something that looks like a Bessel function. And out near the edge of the pool, we very definitely do. We get a nice little node in here about 2/3 of the way, and we start to get a Bessel looking shape here, but our boundary condition is fixed, not sliding, so it pulls it down a little bit. So we need to do a little work on that there. In summary, we have observed a Seiche of about a 6.2 centimeter amplitude and 1.975 seconds. The Seiche is successfully modeled with the cylindrical wave equation using a velocity that's representative of the non-shallow wave environment.